Next thing we got to talk about is the action of a charged particle in a field, electric field. So here what we do just imagine, the easiest way to see this is imagine a plate, two plates. And the way I've drawn this here, I put a potential across them. Hook up a battery. And you know what happens? Current flows until you build up enough charge. Did I put I put the positive on top. Build up enough charge until you've, this is essentially a capacitor, so until you've charged the capacitor. 1 coulomb, by the way, of charge equals the amount of charge stored on a 1 farad capacitor when 1 volt is applied. Okay, that's another way to remember what, so that defines a farad for you, right? You'll see these units on your universal constants or page. They're all related. All right, so what happens here is that you get an electric field This is now an electric field. It's really a vector quantity, but because we're doing this with capacitors are close together, it's just really just these straight lines. And the magnitude of that electric field is the voltage divided by the distance between the plates. This is another very important factor. We can get a high electric field by fixing the voltage and just moving the plates together. Or don't let them touch, but get them very, very close. Now, the force on a charged particle in such a field is given by QE. Pretty simple. Right? So if I put a negative particle in here, the force is in this direction. Moves it towards the positive plate. And if I have a positively charged particle, the force is in this direction. And there's one more very important relationship between charged particles and forces. Oops, wrong one. Oh, this one, not working. So the last one is what's called the Lorentz force. And this is a bit more complicated, but we'll only use it in very simple situations. And this is how a moving charged particle interacts with a magnetic field. So this is, a magnet will affect the motion of a charged particle. And so we have to define on the board here where the magnetic field is. I've chosen the magnetic field to be pointed into the board. That's what this symbol means. Sometimes you see it that's pointed out of the board. The arrow is pointed towards you. This cross is the sort of the quill end of the arrow, right? So the arrow is going into the board. That's the magnetic field. So the Lorentz force is written like this. Again, it's a vector. Here's my charge. This is the velocity of the particle. So I have to pick a direction for it to move. And this is that magnetic field into the board. So this is the situation where we use the right-hand rule. Let's imagine I have a positive particle, and it's moving in this direction with some velocity v. The magnetic field is into the board. Now this thing right here is what we call a cross product. And so you take your right hand, put it where the v is, and turn it to turn it to the B. That tells you where the force is. So on this situation, I'll put it FL for Lorentz force is in that direction. Now, watch, if I have a minus particle, though, moving in exactly the same direction with the same velocity, I'll do the same thing, V into B. It says, well, the force is in this direction, but then I have a minus sign. So it goes boom, like that, bam. And I got the Lorentz force is in this direction. So if I have a mixture of ions moving in this direction and the field's into this, guess what happens? I separate these ions. You know, if I'm they'll follow trajectories that are completely different.